This is a very brief lecture about the role of defects in plastic deformation. So this is just a one slider where I try my best to generalize the introduced concepts and processes a little bit and talk about the general aspects that are related and that play a role when we're speaking of defects taking place in materials. So, and this is right before we move to fracture. So, that will be covered next. What happens when the material breaks down, and that's the final region in the stress strain curve we have encountering the previous lectures. I want to first note that in fact it's the temperature of the solid that really affects its mechanical properties. And well, of course, obviously, like you can imagine that yes, like an electrical cable, the thermal expansion, of course, the temperature of the solid, of course, it matters, so that the thermal expansion takes place. But in addition to that, the temperature of the solid also affects the dynamics that may play a role when we are seeing an effect or defects into the material properties. So what I want to try saying here is that when we have defects in a material, in some of the processes, for example, when we think of a plastic deformation, these defects, the new defects are being generated, and the existing ones, they are moving in the solid. And these processes, they are actually statistical in nature. There's a lot of these defects in a solid, and the kind of approach, the only viable approach how we can mathematically try to tackle this kind of problem is that we take use of statistical analysis, so statistical physics and thermodynamics. And then I want to point to you that if you want to really understand more carefully and more quantitatively what happens in solids, in processes, and in terms of the properties of solids, where defects play a role, you should really be knowledgeable about statistical physics and thermodynamics too, so that you can really see them also as a dynamical processes. And the kind of thumb rule here is that when we go higher in temperature, we have more energy in the system, and this will ease up the dynamics of defects. So the defects, they will move more easily when we have a higher temperature in the solid. So this is the general rule of thumb, and it's quite intuitive when we are kind of thinking that the defects and their dynamics and movements and generation, that they are statistical in nature. Then we can kind of see that we can understand things surprisingly well based on thermodynamics and statistical physics. And some example cases of this kind of a transition in the properties of a solid, that for example, when we move to high enough temperatures, some brittle materials, and I recall brittle material was a material where we did not have a plastic regime, can turn into a ductile material when we just are working in a high enough temperatures. And I think here glass and the many types of glasses, it's actually like a family of materials glass. There's hundreds of glasses, and it's in its own field of science, it seems to me, that at high enough temperatures, glasses, they turn from brittle materials into ductile. And then you can mold them, and that can actually be quite important. And for example, in optics, when we think of lenses, this is the process that we are actually making lenses in reality, so that we are heating up a glass, we are melting it down or almost melting it down, and then we are able to kind of mold the shape of a glass. Another example, because you may have heard of on the internet these days, so most on the internet data communication that is taking place on Earth, it's being transferred via optical fiber communications and optical fibers, and optical fibers have been made by increasing the temperature of glass rods into a level that they're being turned into ductile materials, and then you can actually pull a glass rod into a piece of glass fiber. And when you have a good enough process, you can actually make kilometers long fibers out of glasses, and you can make optical fibers. And then when you put many optical fibers together, you can actually start transmitting information inside pieces of glass optical fibers by just shooting laser light in them, or just normal light. So these are just some examples that the defects, they are quite important, and I wanted to point to you that they're statistical in nature, the dynamics that plays a role in defect formation and movement, and sometimes that is the kind of missing piece of physics that we would need to introduce when we would want to quantitatively understand what happens when we want to calculate things. So this is what I wanted to say, and I'm sorry for being not very quick on it. 1 slide and 6 minutes is not the world record, but hopefully there was also some useful bits of information for you too. Okay, thanks and bye-bye.